Alright, so in this problem we have a solid cylinder that has a mass of 3.5 kilograms and a radius of 30 centimeters, and it's rolling down an incline. So we have a solid cylinder, so fill it in, and it's rolling down an incline. So we have to remember our velocity is in this direction. And this incline has an angle of inclination of 25 degrees, and we want to know what the angular acceleration is about the center of the cylinder. And we are back here given a coefficient of static friction. Now what rolling without slipping means, and we'll talk more about this in detail in the next section of the lecture, is that instead of sliding down the incline, the object is actually rolling, which means technically speaking the point that is in contact with the incline or surface is not actually moving forward. It's actually the rolling motion that causes the motion forward. And we'll discuss that more in detail when we get into the energy section in the next lecture video. Alright, so since we're given a coefficient of static friction, that's probably a good idea to sum our forces. Alright, so we have a force due to gravity of the object. We have a force normal coming up from the surface. So force normal, force due to gravity, and then we have a force of friction that's going to act along the surface. And so what you've seen up here is I've summed forces in the x direction and I've summed my forces in the y direction. Now this is the chapter on torque, and we're attempting to get to angular acceleration. So that means we should also probably look at where we have torques present in the system, because the net torque should cause the net angular acceleration. Now here's the tricky part. Remember, we have torque equaling force times the lever arm, and where our force is applied matters. So that's why I didn't just draw the dot for the free body diagram. I actually drew the cylinder and drew where the forces are actually coming from. Because if we look at our center of our circle, our lever arm essentially is the radius of the circle. So the force normal is parallel to lever arm for the force normal. And the lever arm for the force of gravity is also along it, because it goes along essentially one of the radiuses out of the center from the rotation point. So the force normal and the force of gravity don't actually cause a torque. What does cause a torque, and I'm going to pick a different color here just to emphasize it, is the force due to friction. So this is actually perpendicular in here. So that's why when you look up here, I have the force of friction static times the lever arm or radius of the circle is going to equal the moment of inertia times the angular acceleration. Alright, so my goal here is to solve for this variable here, which means I need a couple of other pieces of information. So I need the moment of inertia. So I went to my list of moment of inertia equations linked in Blackboard and found the moment of inertia of a solid cylinder. And I also need to be able to find then the force of friction, because the radius of the cylinder is given up here in the problem. Alright, so naturally we want to of course go up to the x direction equation, and the problem is we don't know what the acceleration in the x is. And I know this is kind of confusing because even though technically speaking this bottom part here is not sliding forward, it's rolling forward, the system is still traveling forward like this. So a of x is like this. So even though this part is rolling forward rather than sliding forward, the whole system is still moving forward in the x. So there still is a net acceleration in the x, and we don't know what that is. Alright, so that means that we need to go back to our equation over here where the force of friction static equals the coefficient of static friction times the force normal. So we need the force normal. So we have this relationship here, remembering that the object is not moving up and down on the incline. So this is 0, so our force net is our force normal, I should say, equals our force of gravity in the y direction, and force of gravity in the y direction is going to equal mass times g times the cosine of theta. So you can find our force normal, which we can then plug in for force normal down here, and our coefficient is given in the problem. So we can find the force due to friction, which we can then plug in back in our original equation, which I've rewritten over here, plugging in my moment of inertia. So a force of friction times the radius of the solid cylinder equals 1/2 times 3.5 kilograms times the radius squared, so 0.3 meters squared, times the angular acceleration. So our angular acceleration turns out to be 9.18 radians per second squared.